day, ladies and gentlemen, boys, girls, and fellow Homo sapiens. Welcome to the wonderful world of today. I want to talk a little bit about work today. Work, fairly simple concept. You guys go, oh, I got to go into work tonight. Oh, doing that essay is going to be a lot of work. Studying was a lot of work. It's more work than I wanted to put into it. Okay, that's a different kind of work than we're thinking. That's thinking along the lines of effort, something different. Our physics description is slightly different. So, for example, I have this mass, 1 kilogram. Okay, I'm holding it up. Am I doing any work on the mass? Good question. Now, am I applying a force to the mass? The answer is yes. Of course, I have to be applying a force of, let's say, 9.81 newtons. This is a 1 kilogram mass. The force I have to supply is to overcome gravity or to balance it out so it doesn't move. There's no movement here, no acceleration. So I must be applying a force of 9.81 newtons. Am I doing any work? The answer is no. According to our physics definition, for work to be done besides a force, we need a displacement. We need a distance moved. This is not moving anywhere. So according to our definition of work for physics, there is no work being done. Now, if I were to lift this at a constant rate, was there work being done then? The answer is yes. I'm still applying that same force, but now it's moving. Since it's moving, I get to say I've done some work. Now, if you're sitting here holding this, you say, whoa, Mr. Curtis, I'm going to get tired. I must be doing some work. And yes, you are. You're just not doing any work on the mass. Your work is being done on you. Your muscles in here are flexing and moving, but they're moving against the bone. Okay? Moving to hold your thumb in place. But I'm not moving this, so I'm not doing any work on this. Will I get tired doing this? The answer is yes, eventually. Okay, it's not a very big mass. I could probably hold it for a while before I'd really get tired. Different question. If I do this, and move at a constant velocity, did I do any work? And the answer is no. Why? The force I am applying is perpendicular to the motion. Okay, if it's perpendicular to the motion, by our definition, I'm not doing any work. Okay, so let's keep that in mind. So, our definition of work is going to be something like this. Work equals a force. I need to apply a force for there to be work. I need to move it over some distance. And then, because we have this issue with the direction of which I'm applying the force, I throw in an additional term, the cosine of the angle between the force applied and the distance moved. If the force I apply is in the same direction as the displacement, the cosine is 0. And it's simply force and displacement, or distance. If, in that last case, where I'm simply holding the mass up and walking, the force was perpendicular to the displacement, cosine is 90. Cosine of 90 is 0. By our definition, no work done then on the mass. Okay, for those of you that want to be finicky, there was a little bit of work that had to be going to get it moving. Inertia, we had to overcome that. But once we had it moving at a constant velocity, no work. When I stop, a little bit of work has to be done. Okay, but in general, no work because the force being applied was perpendicular to the distance. With that in mind, let's take a look at a couple of example problems. Here we have, number one I'm going to do is a 20 kilogram suitcase is raised 3 meters above a platform by a conveyor belt. How much work is done on the suitcase? Okay, we're going to try to make that one as easy as possible. Let's say the conveyor belt is simply moving it straight up. There's no angle given, so we're just looking at it moving straight up 3 meters. In the second problem, we're going to have a flight attendant pulling her bag 253 meters across the airport floor at a constant velocity. The force she exerts is 40 newtons, and she's exerting at an angle of 52 degrees above the horizontal. We're going to find the following: the work she does on the flight bag, the work done by the force of friction on the flight bag, and the coefficient of friction between the flight bag and the floor. Oh dear, coefficient of friction. Remember, all of this stuff is additive. We keep putting it all together. So we need to be able to have all of these things at our fingertips. That formula sheet, those understandings, you need to keep up with it. So let's take a little look here at how we're going to solve this problem. Okay, things we get to know about that first problem. Well, the mass of the suitcase is 20 kilograms. Given, we know G equals 9.81 meters per second squared. Hope you guys know that one by now. How high did I move it? What distance did it go? It went 3.0 meters. Okay, looking at that, what do I need? I draw my little picture so I know what's going on. I have an applied force going up. I have my force due to gravity acting down. Okay, my upward force, because we're moving at a constant velocity, my upward force must be equal and opposite to the force due to gravity. Simply should be mg. So remember, the sum of the forces here in the y direction are 0. I'm not accelerating up. It didn't give me that information. So if I wasn't given it, we're going to assume that we weren't. Therefore, I know there's no upward acceleration, so this applied force minus the force due to gravity must sum to 0. That means my applied force must equal the force due to gravity, which simply is mg. To find the work, my equation is work equals force times your distance times the cosine of the angle between them. Well, in this case, the cosine of the angle is 0. We're moving in the same direction we're applying the force. The distance is going to be 3 meters. And again, this was 0, so that turns into 1. So my force is simply going to be mg. I'm going to move it times d, and this is going to be the cosine of 0, which goes to 1. So my work on this object is simply 3.0 times, oops, started with the wrong thing. Okay, 20.0 times 9.81 times 3.0. Okay, the unit for work, if it's force, remember that's in newtons, it's a newton meter. And a newton meter, in our case, we call it a joule. Okay, force is newtons, distance in meters, a newton times a meter gives me a joule. We have this, 2 significant figures. As I finish that one, I should get 588.6, I believe, is what I have down. Rounding to 2 sig figs, that means I should have 590 joules. 590 Newton meters. Hopefully that makes a little bit of sense. Okay, so there's the problem. Again, force was applied in the same direction as the displacement, so the cosine of the angle between the two is 0. Notice, if the displacement is opposite, or the distance moved is completely opposite the direction it was being, the force was being applied, the cosine of 180 is -1. All of a sudden we can have negative work being done. Okay. The next problem we're going to look at is that problem we had listed that had the flight attendant moving her bag. Okay, so we have the force due to gravity, which is the weight of the bag, which should be 70.0 newtons. Okay, the distance we moved, 253 meters. The applied force on the bag is simply 40.0 newtons. We know gravity, 9.81 meters per second squared. And we know the angle between the force applied and the distance moved is going to be 52 degrees above the horizontal. Okay, first we want to find the work done by our flight attendant on the bag. Starting from my picture, I've got a simple picture. Here's my force applied. Here's my normal force. Okay, here's my force due to gravity. Here's my force due to friction. These are all the forces applied. Now, some of you probably already noticed, hey, this isn't as big as this. Well, there's a reason. This applied force, remember, is going to add into this upward force, and it's going to supply what's left to make these two things equal. Okay, I didn't draw it quite to scale. Sorry about that. We see an angle. Remember, we're picking our axes to be this way. Positive y is up, positive x. So we have positive y up, positive x to, in our case, to the right. Just call that forward. We're going to break the one force that isn't along the axes down into the axes components. So we have a force applied in the x direction, and we have a force applied in the y direction. This is theta, so this is simply the applied force, cosine of theta. This here is simply what? It's the applied force, sine of theta. Okay, our formula, very straightforward. Work equals the force applied times the distance times the cosine of the angle between them. Okay, what direction are we moving? Well, we're not lifting the bag up. So I'm saying that the force in the y direction is going to balance this, but there's no acceleration. There is no movement upwards. There is no work in the y direction. The work, if we have any, has to be in the x direction. That's the only direction we have any movement. So, this is the force applied, d, cosine of the angle between them. Well, notice, force applied and the cosine of the angle between them is simply the force applied in the x direction. So this turns out to be the force applied x direction times d. This is exactly in the direction of this. So notice that. So what do we have? Just going to go backwards here and say the force applied, that is 40.0 newtons times 253 meters times the cosine of 52.0. Again, if you wanted to try this before I got this far, all you had to do was stop the video, give it a shot. I recommend that. Okay, we have this. Simple work. Hopefully I did my calculation correctly. Should give me 6230.49413, and that's in joules. 3 sig figs, 3 sig figs, 3 sig figs. Function should return 3 sig figs. It's all multiplication. No real trouble here. I should be good to 3 sig figs, which in this case is to the tens place. So my answer would be 6230 joules. We could also write that as 6.23 times 10 to the third joules, which we could also write, if we wanted to be fun, 6.23 kilojoules. All acceptable answers there. So that was A. So we're going to put A over here, or 1, I can't remember which way I listed it, is going to be 6.23 times 10 to the third joules. Next step, force of friction. What what is the force of friction going to be equal to? Well, we take a quick look now. If I've got this force, the force of friction, I'm going to look at the sum of the forces in the x direction, which are going to be 0. I am not accelerating.